Well, good morning and or good afternoon, everyone, depending on your location. We've still got some folks logging in here to the webinar, and hopefully everyone is able to do so efficiently and without too much headache. We'll go ahead and get started here as we are 2 minutes past the hour. Thanks again to everyone in attendance here today. We've got a good, diverse list of attendees here from different markets. A lot of pipeline folks, a lot of DOT folks, and folks from other industries and segments as well. And so we'll go ahead and get started here. Little bit of housekeeping, just as a reminder, this session is being recorded. So we will make this webinar available, the video available as soon as possible after conclusion. So do feel free, you'll get follow-up email. Feel free to share coworkers, colleagues, and so on. All lines are muted. We do hope that you've got some questions that you'd like to ask throughout the presentation. If so, please use the menu on the bottom right to ask those questions, and we will do our best to answer all of them here in the last 5 minutes or so of the session. I am Jake Opdahl. I'm the Director of Sales here at Teren. Today's webinar, I'll be joined by my colleagues Ben Lowry and John Norman. My background is in GIS and remote sensing, business development typically for most of my career, and much of that focused in the pipeline space. I'm very excited to have my colleagues with me here today. You'll be hearing from John Norman, our Director of R&D. Tremendous amount of experience in spatial ecology, all things GIS and remote sensing, soil science, geomorphology, and behind a lot of the analytics that we'll dive in here to today, as well as my colleague Ben Lowry. Again, tremendous amount of experience in the sensor space, focused on LiDAR, remote sensing, as well as IoT, GIS and geospatial in general as well. So you'll be hearing from both of them here in a moment. But for now, you're stuck with me for a little bit here. Quick review of the agenda. We'll be going through some of the objectives and kind of key concepts here to kick things off. We'll review this concept of the environmental twin. We talked about this in our previous webinar. We'll talk about it here again today. And in regards to that previous webinar, we will do a little bit of a review for those of you who are unable to attend or who have not seen the video, or just as a refresher here, because it does tie in again into this series of webinars, right? The examples we're giving here in the context of what we covered last time. So we'll do a brief review on that, which of course will segue into what comes next, which is where we'll focus here today, which is really getting into leveraging these high fidelity data sources to identify, to measure, to prioritize, monitor, and report on these different environmental threats. There will be some demonstrations throughout leveraging our data and our technology here to help kind of tell this story and communicate what we're talking about and showing here. And then we'll hopefully have some time for review and for some Q&A at the end. So as we dive in here, who is this for? Well, certainly there are personas or roles and responsibilities where we interact a lot with the companies and organizations we work with, from the GIS departments, integrity, risk, the geotechnical engineers, and then this always has some form of operational component. So operations, maybe leveraging this data, the analytics, the decisions that are coming out of this, as well as the engineering services and executives as well. But if you really look at this at a high level, right, anyone or any organization that is managing a physical asset that may be subject to environmental risk or protecting the environment from that asset, in either case, what we have found is that there are means in which we do this, leveraging large, complex data sources. So how do we turn that into something usable? How do we help organizations make that into something actionable, decision-ready analytics? And so for any owner, operator, organization working with those physical assets subject to these environmental risks, or again, environment at risk from potential from the assets themselves. This is for you. With that, my guess is that everyone who has joined here today is very well aware of these environmental threats. And these are no longer force majeure type of things here. When we look at landslides, debris flow from post-wildfire, the historic rains and climatic events that we see, these events happen more and more. There's more and more growth of the physical assets that we utilize, whether it's a pipeline or a roadway or a structure. And so that interface between these different environmental factors and these assets certainly is not going away. And so companies are trying to find ways to better manage and mitigate against these potential environmental threats. So you're here at our Teren webinar. We're going to focus a bit on our approach and what we've done here. And as I mentioned, this concept of the environmental twin, something we talked about in the previous webinar. I'm guessing everyone on this webinar here today has certainly heard of a digital twin. Very common term, often utilized to create these digital representations of physical assets such as a building, such as a bridge, right? Well, this same concept of leveraging technology, leveraging data, leveraging sensors and the data that is derived from there to create these digital representations, we're doing the same thing from an environmental perspective. We are looking at the environment that is interfacing or near those assets and creating an environmental twin in a very similar sense. And we're doing that by utilizing a number of different data sources, taking that data, combining them, and utilizing that information to derive, again, these key analytics or these decision points, this data then that can really be utilized. And so from a data perspective, we're looking at environmental data, which the terrain on which that asset is located, climatic data, looking at precipitation, looking at soils information, the information we're pulling from these sensors. We'll talk today a little bit about LiDAR, but that can include other sensor types. It can include satellite imagery. It can include other IoT devices, bringing all of that data together. And again, then where does that intersect with the infrastructure data? Roads, pipelines, structures, whatever that might be, right? And so if you joined us in the previous webinar, really where we focused was kind of on this assess component, right? And this really is all more circular per se than linear, right? Because this is a repeat process often from an assessment, prioritize, monitoring certainly has a temporal component over time and how we report. So we'll touch again on some of the concepts from the previous webinar around assessment, but we'll really be diving in then on how we use that data, working with our customers to then prioritize where to apply additional resources, where to acquire high fidelity data, how we can take that information then to help identify, prioritize, and monitor and report over time. So, quick review from our previous webinar, and we will put the link, the YouTube link in the chat. If one of my colleagues, Ben, if you wouldn't mind maybe posting that in the chat while I'm chatting here with our attendees, please do feel free to share that again. Really what we focused on in part one of this webinar series was looking at the Teren Essentials platform and the data that makes up that solution to help operators identify various weather and external force threats at a very broad brush assessment, right? And so working within industry to develop and understand what those needs are, what those risks are and why, and where we need to monitor those risks, right? We can take this information, and I'll give a little bit of a review here when I jump into the demo as well. But taking that broad brush approach, right, and what we looked at last time was utilizing that data in the example of a pipeline operator to take something, for example, 10,000 miles of pipeline right away, and finding where the highest risk was or is, in this case, around landslides, to determine where to take that next step, where to allocate those resources, where to go acquire high fidelity LiDAR data and perform this analysis. And so we'll be taking that baton and kind of carrying that forward here in today's presentation after the prioritization, utilizing this broad brush approach, right, to leverage that data to inform and prioritize those areas of concern. The other use case we talked about, again, was leveraging this data to inform a risk model, right? And so that's another area we'd be happy to chat with folks if there's interest there, looking at those different threat and susceptibility layers. So last time we focused in on landslide threats, and we'll be carrying that forward in the example here today. But again, this example could apply to subsidence, looking at karst topography. It could apply to flooding, be it inland or coastal. It could apply to wildfire. It can apply to depth of cover due to loss of soil from agricultural practices, due to loss from on tertiary roadways, whatever that might be. Same concept, right? But today we'll utilize this in the context of a landslide, right? So you can see in the left the nationwide landslide potential model at a 10-meter resolution. And you can see throughout the US, the red being the higher risk, green being lower risk, certainly Appalachia, the Rocky Mountains, Ozarks, but really sprinkled throughout, we can pinpoint that risk. And utilizing that data, which has been statistically validated, we can take that and then again start to prioritize, right? Where is this highest risk? Because we know that as a asset manager, as an asset owner, the resources are limited, whether it be budget, whether it be time, whether it be the human resources, right? So how do we prioritize? And so utilizing this example from a landslide perspective, which we'll cover a little bit more here in just a moment in the demo, this is helping us prioritize, take that next step, which is where we'll put a lot of focus here today. That output, right, when we take that broad scale assessment and we intersect that with an asset, and be it a roadway, be it a pipeline, we now can start to both visualize, as we see in the slide here, red, high threat, orange, medium, green, low, in a dynamically segmented, linear referenced output. In that sliding mile, we can start to see a percentile risk category that we can start to utilize. All of this backed in the attribute table again, right? But from a visual perspective, we can start to see where those areas of high risk are. And again, that will help inform where we apply additional resources in those next steps. In this example, again, we've taken that information from a large geography, thousands of miles of pipeline. Leveraging this information, we can now pinpoint, say, 80% and above threat, right? And we can start to take from that information to really drive what those next steps are. So visually speaking here, you can see on the far left, a lot of pipeline. We've started to pick that apart and piece that out into those areas of high risk, which now we can start to utilize, for example, for flight planning. LiDAR acquisition is expensive, so how can we reduce that footprint, reduce that cost, but also be focusing in those areas of high risk? So once that prioritization has happened, right, we can prioritize those geographies for further inspection or data acquisition. We can now work to figure out what is the right tool for the job. What are those data inputs or sensor types that we might utilize? In the example we'll give here today, the right tool for the job is high fidelity LiDAR. So that may be something that we at Teren are tasked to do by working with our strategic partners in the aerial acquisition space to go acquire that high fidelity data. It may be something you've already got sitting on the shelves, right? Sitting on a hard drive. Very often we see that where we work with large organizations that may have already purchased LiDAR data, and that's fine. We are certainly not restricted to going out and acquiring that ourselves. We're really agnostic on consuming that data to get to these answers. because really where the rubber meets the road there is the analysis of this data. And again, with this focus on identification, right? Previously in part one and in the review I just talked about, we're looking at a percent risk along an area, in an area or along a line. Well, we're now moving into the analysis to actually identify and delineate, as well as prioritize, and then put a monitoring process in place. And my colleague will dive into that here in a moment. And then with that, going beyond just hucking red pixels over the fence and saying, here you go, how can we help integrate that data to utilize that in the ways in which you need for the right stakeholders, the right use cases, again, all driving towards providing these very actionable decisions. So before I hand it over to my colleague here, I do want to give a real quick demonstration to kind of set the stage. And again, you're going to be seeing similar information here at a greater detail when John dives in, and then when Ben comes in, we'll be looking at some other facets as well of the technology. But as a bit of a review and kind of setting the stage here, again, looking here, this is again really kind of part of the review from part one, where we see in this case the landslide threat layer across the lower 48. Right now, as we talked about, once that data has been intersected with a particular asset, in this case, if I turn this off, we've got a use case or an example data set here in the Appalachian region, where that data has been intersected with the asset, and we can again start to see the visualization here. If I look at the legend, again, that percentile category of risk of a landslide occurrence. So in this case, boiling it down from a nationwide or a very large geography, we've boiled it down in this example to this particular area of interest, right? You can see it's all red and orange. So this is an area in this example where the client would say, all right, this is an area where we need to budget and apply resources to utilizing fidelity data to take that next step. And so, as I've mentioned, in this case, that may be high fidelity LiDAR, right? So if I zoom in a bit further, I believe I've already got that turned on, you can now start to see this hillshade, right? And so this is derived from that LiDAR data. So what you're seeing here, a digital terrain model where we can take that LiDAR data, and again, not really going in depth on these different data sources, but LiDAR, one of the true powers there is the ability to remove the vegetation, the anthropomorphic features to get down to this bare earth representation. Again, a key part of that digital twin concept is now we have a digital twin of the surface, the bare surface of the earth in that location. Because of the high fidelity of the measurement values we can get from LiDAR, we can now start to utilize this for analysis to not only find, but then to prioritize the particular geohazards in this case. So from that LiDAR data, our analysis process, and if I zoom out a little bit, you can see here, hopefully on screen, and I'll zoom in here in a moment, but a number of these features that have been delineated, right? These geohazards, in this case, landslides. Now, very quickly, in a simplistic type of example, if I open up this attribute table, John's going to get into, the meat here of this ranking and prioritization, but at a simple level, we're utilizing these measurement values to prioritize these assets in an absolute ranking system of 1 to 10, 10 being the riskiest. So I can come in here, for example, and sort on this table on this particular column for rank and say, all right, I'm going to go start with these number 10s. Those we know are the highest risk, right? And so if I zoom that result, I can see here, I'll zoom out just a little bit. And I can start even with this really desktop assessment in this 3D view to start to see how these particular hazards interact with my asset. I'm not going to dive in too deep here because John will be covering this, but then we start to look at the hydrology, surface hydrology. Where is it in relation to the asset, to the pipeline, right? We can really start to get to this information, which is all driving towards those actionable decisions, right? Where do I send my field crews? Where do I spend my mitigation budget money? What is that highest priority? So with that, I'm going to hand it over to John, who will be going into much further detail on this, and we'll go from there. Take it away, John.
Thanks, Jake. Transitioning to my slides here. So Teren Analytics. Can everyone see my screen okay?
Yes, John.
Okay, perfect. Let me transition here. So just kind of off the top here, this slide is just showing that digital twin, and where we are able to take, and when you look over on the left-hand side here, you have an image where you have geohazards below those landslides. In this case, they're not really evident within that imagery within a patrol flight, but once we're able to then acquire LiDAR or utilize LiDAR, we can actually then strip away that vegetation, and then you can actually see over on the right-hand side those landslide features that then we use to analyze against a given asset. Going forward, here's a zoomed-in scape of a hillshade with a pipeline at the bottom, and that delineated that white line. This is where we then start to then identify those features and then rank those features as a function of their morphology, the steepness of the hill slope, the hydrology that's driving them, and their directionality to that asset. In the case of these two features, these are two identified landslide features. One is actually intersecting the pipeline, and one is just above the pipeline. These then get different ranking systems based on their geometries and their morphologies to that asset. The landslide on the left-hand side is a intersecting the pipeline and getting a higher ranking value, which I'll go through in a second, of those attributes. But that's how we then take this data and then make it actionable. Within that process, this image is showing when we delineate a landslide, we also are figuring out the morphologies of that landslide. So where are the scarp slopes in the red area, that the top of the hill slope or top of this feature where it's actually becoming disconnected from the greater terrain, and then where it's accumulating into those toe slopes, the green areas. Those all become part of what we attribute a given landslide along an asset right away. And then we actually then start to then analyze its the amount of material, the steepness of it, the amount of connectivity to that asset. Another component of our ranking system, which I'll go through in a second, is this directionality. Is it moving towards the asset, or moving away from the asset, or moving along the asset? We represent this in degrees of impact. That then all feeds into a decision tree that then gives us the ability to then come up with that absolute ranking that Jake had mentioned. That decision tree has a hierarchy associated with it. The first step is how close is it to the asset? Is it intersecting the asset? Is it below the asset? How is it intersecting with the asset? And then we start to look at the morphologies in the case of a landslide. Is the scarp slope, toe slope interacting with the asset? Is it moving towards or away from the asset? How steep is that feature, that landslide component to the asset? And so is it on a very steep hill slope? Is there a lot of potential there? And then we start looking at its shape. Is it a rotational slump? Is it translational slump? And then we actually then drill down to eventually how large is that feature? Is it a very small feature, or is it a very large feature? As Jake had mentioned, within the analytics is the hydrology. So in the Appalachia region, obviously, hydrology is very important. So within the pipeline right away, we start to assess, is it being dewatered properly? So in the sense of liquefaction, in the sense of the things that actually drive these features, hydrology matters. And so in the case here, we can then start to assess, is the right-of-way being properly dewatered? Over on the right-hand side here, you can see the right-of-way with the pipeline moving through it, and you can see the water bars actually moving the water from that right-of-way and then moving it to an off right-of-way situation that then allows that right-of-way to be less acceptable to landslides via liquefaction. Over on the left-hand side, you'll see water bars that are in there, and you can kind of faintly see them, but you can see that there's a lot more saturation going on here, and that right-of-way is not being dewatered properly. That then allows us to then assess not only what is driving a landslide, but where areas are vulnerable to landslides via hydrologic processes. What I'm going to go through here just briefly, and then I'll move into a demo situation, but just also the digital twin concept and then monitoring that through time. So on the left-hand side, we have just a hillshade with a pipeline moving through that right away. You can see down in this lower right-hand section a disturbance within that hillshade, actually that is then delineated or identified as a slip or landslide. When we look at the far right-hand side, we can see that this right-of-way is not being properly dewatered, and that you have a lot of saturation on a very steep hill slope that is driving that landslide. As we move through time two, you can see that now that landslide has propagated laterally towards that pipeline. So initially it was a hazard level 3 because it's still on the right-of-way, but it's moving along the right-of-way and not actually towards it. But then time 2, it's propagated laterally, and it's actually now intersecting that pipeline, which bumps it to a hazard level 6. And you can see that it's actually becoming larger and intersecting the pipeline, and that effective hydrology is changing, even though the upslope hydrology is still constant, and it is actually what is driving that landslide. This slide here shows the difference between the time 1, time 2, where we actually then are able to identify where in that particular component of that landslide has changed the most. And you can see that then as through time, as we identify these hazards, we also want to assess how the rate of change that is occurring, and that is what our change detection is targeted towards. And then you can see these problematic flow paths, which are saying that there's off right-of-way hydrology driving this, and then on right-of-way hydrology driving that. I'm going to now go into a demo for within our viewer. So as Jake had shown here, where we have our landslide susceptibility, our area of interest, go into a couple instances here where we have a hazard level 10, those two landslides that Jake had shown previously, and walk through some of the attributes here. So you have these are the top, and within this AOI hazard level 10s. If I actually click on them, as Jake had shown, what we do within this absolute hazard ranking system, we evaluate multiple components of that landslide in regard to the asset of interest. One of the biggest components of it is how steep of a hill slope is it on. So we record its average slope that it's on in degrees. The shape of it, so it's more ovate or more round, more of a rotational slump or transitional slump. What we're not showing in this viewer instance is the scarp slope. So at the top of these landslides are the scarp slopes. Those are where it's failing from, and then where it's propagating to the toe slopes. We record the height of those scarp slopes, and we actually then through time document how those scarp slopes are changing. Are they becoming bigger? Are they moving upslope? Or are they the directionality of them? We do the same with the toe slope. So is the toe slope on top of the pipeline, above the pipeline, or below the pipeline? We look at the hydrology. So how much hydrology is driving that feature? Is it towards the ridge line? Is it towards the middle of the hill slope, or is it towards the bottom of the slope? and the factors that can be done to actually mitigate those. And then we have our impact angle. So in the case of these two slides, they are moving more perpendicular to the landslide or to the pipeline, which then bumps up its hazard level. And then at the end, we then document all of the conditions in a common delimited form in that same hierarchy that I had presented. So then you can actually see the factors that go into that ranking system that then result in a hazard level 10. Just to go through a couple more instances here, going to a hazard level 9, which is right here. It is not as big as those two landslides. It's running more along the pipeline, not towards the pipeline. But then this particular instance allows us to then start to look at change detection. So here is our change detection product. You can see within this hazard level 9 feature that it's actually changing from time 1 to time 2. So it's more active. It's more threatening because it's actively moving and causing strain onto that pipeline. So that is a hazard 9. It's intersecting. It's above the pipe, or it's moving along the pipeline, and then there's active change. If I look at a hazard level 6, here it is intersecting the pipeline. There's a decent amount above it, maybe 15% above the pipeline that's moving. It's on a much more gentle hill slope, and so its hazard level, it is intersecting the pipeline. Its hazard level is lower because of slope and the degree of intersect. Moving to a hazard level 5, this is where then we're getting into some of these off right-of-way conditions or areas where it's not actually intersecting the pipeline. This is a hazard level 5. It's above the pipeline, so it is posing a threat to the pipeline. It's not directly intersecting the pipeline, but it is in that medium priority. Moving to a hazard level 4, this one is below the pipeline. If I actually even turn off the hill shade here, this is where our change detection product comes into play. Even though it's 4, it's active, and there is actually change going on. You can see from the 2 time periods that you have a situation where you have a scarp slope developing and a toe slope. So this is gaining. It's still a 4 because it's still on the right of way, but it's not actively intersecting the pipeline, and it's below the pipeline. But this is where when you go into these instances of this ranking system, which is static, looking at just the geometries and the components of that feature, but when you utilize and integrate the change detection, you can actually then start to see, wow, this thing is actually, maybe it's a 4, but it's actively moving, and you can back it through time and focus your resources there. Going to a hazard level 3, this is a situation where you have an active landslide that is still slightly on the right of way. It's moving along the pipeline, so its threat level is less than that 4, which is directly below it, moving down slope of it. But in this case, in the sense of a roadway condition, for this pipeline, it's a 3, but for this road, it might be an 8 because it is actively degrading, moving up slope of that road and causing and providing or actually interacting with the road and generating a potential hazard for that roadway. And then if we go to it, just the lowest ranking, which is a 1, and this is in regard to the pipeline itself, it's completely off right away. It's not really posing much of a hazard. It's moving more down slope and really doesn't have the potential to actually interact with the pipeline. But in the case of this roadway, it is a hazard to this road because it's directly above it, and it has the potential to move down slope onto the road. If we look at the hydrology model here, and we look at flow paths, the flow paths basically are saying that it's going to move laterally or longitudinally down slope and then move on to this roadway. So when we are doing these ranking systems, we are taking the asset into account. In the case of this pipeline, this is very low risk, but in case of this road, it's a much higher risk because it has the potential to actually propagate and then move on to that roadway. Some other examples here of they're more road focused that we've identified within our content region. Here's a highway, for instance, and here these have been delineated as earth movement components, places where you have slumping and triggering of a landslide that then are directly adjacent upslope of that road and pose a threat to that road, either if you're the highway below it or the road above it, where you're going to then propagate back up into that road and then start compromising the integrity of that road. More change detection product here for us. So in the sense of pipeline integrity or pipeline monitoring, this is active construction that was occurring onto this pipeline that we then pick up from time 1 to time 2. I'll turn off the change detection product here. But just kind of looking through those instances of this digital twin. So time 1, so here's time 1, and then time 2, where active construction was occurring, and then we pick that up and then the change detection product, and then provide those results of losing and gaining in the sense of either elevation losing and gaining or volume metrics losing and gaining. Moving into the final example for a pipeline integrity management situation, where you have encroachment right away. In the case of this road that in time 1 was not there, that someone built in time 2, that integrity managers are concerned about for depth of cover issues or impacts to their pipeline. That's what we are measuring here. So with that, I will turn it back over to Ben, and I thank you for your precipitation anyway.
That's well spoken. Okay, I am going to also share a screen here. Pick up where John left off. So, what I really appreciate about that kind of overview, John, walking through is, that process of prioritization. So, we have a data set that we are collecting hundreds of terabytes, if not petabytes of data, and collecting information about individual slip locations or hazard locations. And that just involves, it creates this possibility of having to sift through all of those different hazards and then be able to order them into a part of your organization so that your operations are able to plan for that. So it's as important to identify, hold on just a second. I had a report on sharing my screen. Oh, here we go. Thanks, guys. There we go. Got it. Okay. We've got the screen up and going now. Thanks for that. Sorry about the stop. So as I was saying, it's as important to be able to identify the high-ranking risks as it is your low-ranking ones, because you're able to then pour resources towards those and then monitor them through time. So we all know, that the Earth is a changing environment, and so we can watch that asset through time and be able to adjust how we're prioritizing, how we're resourcing field teams, remediation, mitigation accordingly. And that's the kind of job that taking this into the operational context is really required. Is that, yes, we've identified the top 10 most important areas, but we've also said we have our hands around the entire holistic understanding, a comprehensive understanding of our asset and what hazards are intersecting with. And that's a really powerful thing to be able to deliver in an organization. So, having the data stored in an environmental twin allows for that kind of fidelity to be and comprehensive, holistic approach to be accomplished. So that it's not just, we focused on landslides in some of the examples here today in hydrology, but we can go into cut banks, river scour, subsidence, anywhere that surface is changing, anywhere that we have more information, we can put that into the algorithm for ranking and be able to adjust it as it goes. Because as the Earth continues to meet changing conditions, the environmental twin will need to mirror that. And placing it into this context of integrating it into your organization is really important. So while we have different viewers that have views and can put things into 3D, be able to walk through, as we've seen today in our demonstrations, we also want to federate that data into GIS organizations within the customers that we're working with, so that there's a lot of balance and mutual visibility of the layers and the ability to consume our data. Because one of the concepts, the most important concepts about digital twins and this environmental twin, is that the more data that you're adding into it, the more valuable that system is becoming. And just a kind of peek behind the curtain here on the back end of how Teren accomplishes this. So we've built a platform within a cloud computing environment to be able to process this data that is a novel approach to bringing in big data and big LiDAR data sets. These traditionally have been processed on individual bare iron servers and high performance computing machines at the desktop, but putting it into a cloud environment is really enabling this larger picture to be able to process at speed and scale. So when data is coming in, we can parallelize the processing of that data and take these very large data sets and start intersecting them in ways that we just previously have been unable to do at that sort of speed and scale. So the concept of the environmental twin really hinges, I think, in this day and age, in the ability to do your entire geography, your entire asset footprint, not just take bits and bytes out of it, but really be able to categorize your entire geography as to where it falls in the risk, the relative risk to your asset. So, we have more detail on that if you guys have questions, but it's something that we're really proud of, and it has really enabled us to ask different kinds of questions with all sorts of different kinds of data and applications. But again, the environmental twin is the take-home message here today, is that building an environmental twin enables you to ask different types of questions about your asset and the environment that it's subject to. And bringing in more data sets from remote sensing is certainly valuable. Being able to cross-reference that against as-built plans and reports of installations, that's where then this really starts to take off as a force multiplier to understanding the risk to your asset. And I'm going to demonstrate that in a little bit of a tease here today, with where it really hits home about how the environmental twin can be used. John and Jake presented a great overview of the capabilities that we have to be able to ask large, broad brush questions about landslide risk and other risks from our Essentials platform. And John presented the detailed view of hydrology and how we can look at individual landslips through time. But this is something we're really excited about, and very interested in working with customers to refine. But we have the ability to intersect all of that digital twin, environmental twin data now with weather monitoring. So we have hooks into National Weather Service and other weather services that are able to look at as observed precipitations and start to then generate insight as to what's happening and what's causing those assets to be at risk. So being able to alert and alarm off of an event that comes through is a critical function in this, so that now it's not just a static environmental twin that is waiting for the next update or a reflight or the sensor to update, but we're actually bringing life to that data by intersecting the asset with the known as observed precipitations. So we can institute severe weather alerts. We can look at forecasting. We can look at historical deviations from norms, and get individualized alerts for that specific asset with a pinpoint to where the impact is occurring. So I'll just share my screen here on a demo of that. It's a quick little peek. Again, here you see this is the landslide threat layer that we have with also some assets identified running through it, both the center line and some identified geohazards running into it if I zoom in. But I'm going to turn off that layer, and I'm going to turn on a 3-day accumulation data set for that area. And this is for just 2 days ago. So we have a subscription to these services that allows us to aggregate and consolidate these, and then start creating derived products of the results. So 3-day accumulations, 1-day accumulations, setting thresholds, being able to set alarms and alerts is now possible for every single asset, every single mile of asset in the case of a linear one, and then also monitor the changes to those assets over time. So as we walk through different events that are occurring, if you have a hurricane landfall coming through, like what we saw in Ophelia this late summer, to whatever might be coming down the road, whether it be historical deviations from norm or dry areas where we're seeing suddenly areas that aren't receiving as much precipitation as they have in the past, and so therefore can be deprioritized. So it's really an example of how this is coming to life from an operational perspective, and how valuable it is to have spatially and temporally referenced data in that you can start to ask more questions about your asset. So more on that later. We'll make this a full-blown webinar coming up, I'm sure. So that's our kind of preview of what's to come with Teren. But I'm going to stop there and turn the conclusion back over to Jake to wrap up the conversation.
Thank you, Ben. And thank you, John. We've got about 9 minutes left here in our allotted time. A quick little review before we jump into questions here. I know we covered a lot of information, but I think some of the key takeaways here, right? When we look back at part one from that broad scale assessment where we can start to pinpoint areas of risk, The tools that can be utilized, the data types that can be utilized. In this case, we looked at how we leverage LiDAR data, right, to derive then these analytics from that rich and robust LiDAR data set. There's a lot of measurement values we can tease out of this. All right, so for today, we focused on landslides. As Ben mentioned, and as John showed in his demo, there are a number of other analytics that can be pulled from this type of data. Many of them definitely correlate, such as the hydrology, looking at problematic surface hydrology and how that interacts with a landslide or a slip. We've been working with operators to leverage this data for vegetative classification. So going beyond what you could see visual line of sight, whether that's an aerial patrol or leveraging something like satellite data or orthorectified imagery. With LiDAR data, again, in this case, the ability to pull more measurement values, in this case, the Z values, right, because of that penetrative capability of those sensors, we can start to classify based on even individual trees. So there's a lot that can be pulled out of this, and a lot of this comes down to working with you, our clients, those in the industry, to understand how to best leverage this data. And as Ben had mentioned, taking it a step further, so we can look broad scale, we can then begin to identify, and then over time we can be monitoring. That temporal component may typically includes multiple acquisitions of LiDAR data sets. But then again, we can go a step further and start to look at more near real-time data that will interact with and correlate with some of that information, such as deviation from normal precipitation or high precipitation events, where they are spatially located in relation to your assets or in relation to those particular geohazards. Some things we didn't cover here today that have been covered in other presentations are, again, taking other data sets. In the case in the pipeline industry, leveraging ILI and IMU data to then again correlate where we see bend strain, where do we see a depth of cover issue, and how can we work with that and these data sources to again tease out more information to help operators and managers of these physical assets manage and mitigate these environmental risks. And all that really, again, boiling down to this concept of an environmental twin, having these digital representations that go beyond a pretty picture, but the actual measurement values and the data and the attribution behind that, that again really comes down to a lot of the power of GIS, of geospatial technology, and bringing all of this together. With that, we do have some questions and some time to cover those. So I'm going to work through a few of these here. And again, if there are other questions for those of you who are with us here today, you can enter them either in the chat or the Q&A box down at the lower right-hand corner of your interface for this particular webinar. So a question came up regarding the update cadence. And in this case, in relation to the base data set, the LiDAR data that we're utilizing. I think there's a couple of questions here, so I can probably address a couple of these at once. So what you saw in the demo here today and what is typical for example for our pipeline operator customers, most of them are utilizing a twice a year acquisition. Now, one of the keys with LiDAR is for it to be truly effective. We collect that data or others collect that data during leaf off conditions. So the spring and the fall, so that laser can penetrate through the canopy. We can get those returns from bare earth and or anything else that it's going to hit along the way to get that true representation, right, without a bunch of noise. So spring and fall are those typical acquisition times. Most of our customers are leveraging those twice a year acquisitions and analytic packages. That being said, we do have use cases where it's once a year. We've even had a customer that did a particular area once every other year. A lot of that, of course, driven by the particular environmental risks and threats that are present in that particular geography may dictate how often that is collected. The flip side of that as well is that when we look at things like near real-time data sources such as weather, and we look at some of the new regulatory components, in particular in the pipeline industry around weather and some of the requirements for inspection, albeit that may be visual from an airplane, it may be boots on the ground, but there are other capabilities to then go acquire more LiDAR, right? And in a right-of-way scenario, perhaps the leaf off may not make so much of a difference. So there could be some near real-time data acquisition. And then, of course, looking at other data sources, right? Again, we talked a lot about LiDAR here today, but there are other data sources that can be leveraged that may be more near real-time capable as well. So there's a lot of flexibility there, but the examples you saw typically are based on a kind of every 6 month, twice a year. Another question that came up regarding the landslides and the ranking, and if they would be characterized with an asset value that is then trackable going forward. So if I understand that question correctly, yes. One thing that we didn't really get into here today is this ongoing bi-directional type of interface as well, where we may deliver this information, help integrate that information and digest it into internal systems. That change over time is going to be tracked. So for example, each time we deliver for many of our customers, that geohazard layer is broken into, for example, new, persistent, or resolved, right? So we may have delivered a ranking number 10 landslide. You got out there, you mitigated it, you fixed it. It's been flagged as such. It's still maintained in the database moving forward, but now you can filter on these things to say, only show me the new ones. Only show me the persistent ones. And we can take that a bit further. And, you know, as Ben alluded to, some of the work we're doing with our customers to take this data, refine not only the prioritization workflows, you know, because again, the information John shared on that decision tree, right, will get you so far, but we definitely work with our customers to tweak that and refine that so that again, we have this bi-directional information. It's persisting over time, it's changing over time, and you can maintain and work with that data. Let's see here. There was a question regarding precipitation cumulative of X then tag in LiDAR acquisition, input into the system, or I have to wait 6 months. So if I understand this question correctly, again, the LiDAR data may be updated every 6 months. The weather information, depending on the type of implementation you would look at, could be daily. Right. And so again, you've identified a geohazard. That likely isn't going to change significantly in most cases daily. However, a major precipitation event may be something that then drives that geomorphology and drives that slip to move or to activate. Right. So the weather information can be daily. In some cases, it may be a monthly summary. And then, of course, we could be looking at integrating other data sources, right? Be it from a satellite, INSAR, SAR technology, things of that nature, to see how that could complement some of this base data. A lot of R&D has gone into looking at these different data sources, and that's why we leverage LiDAR. It's the right tool for this job, but we certainly see a lot of capability in supplementing that with other data sources as well. Hopefully that answered that question. And a similar question around the weather and precipitation. Can those alerts be set up to alert in near real time? Yes, depending on the thresholds, right, that we would put in place at that daily level where we're looking at this, it would be updating daily. So if we hit that threshold, for example, geofenced a particular geohazard of concern, storm comes through, we're scraping that data daily on the actual precip, and if it hits that threshold, for example, a email would be generated with that information, a link to a viewer very similar to what you saw, so that information is in very near real time. I think we are about out. For those of you who have stuck around, thank you so much. I've got one more question here that I'll address for those that can stay, but I do want to thank all of you for joining us here today. Hopefully this information was useful. The recording will be provided as well for those that couldn't attend, but as well for those that did that want to share this internally. One more question that has come up around the ranking system as it relates to a roadway versus a pipeline. In the examples we gave today, I know it was very pipeline focused. We do have several DOTs represented with us here today. And in some of those conversations, something similar has come up. That ranking system, while it is probably very similar to how you might want to apply a ranking system to in regards to a roadway, there's a lot of flexibility, and that's actually something we're working with a couple of different DOTs as they look at the current ranking system and how that might be tweaked and modified. Again, at a high level, we have all of this measurement data. There's many ways we can dissect it and digest it. And so that's something, again, that could be applied in particular use cases, albeit for a DOT, for a utility, whatever that might be. And with that, I know, again, we're over time. I think hopefully I covered all of those questions. Any other questions, always feel free to reach out to any of us here at Teren. We're happy to discuss this. We all love nerding out on geospatial stuff all the time. So again, thank you so much, and keep on the lookout for our next webinars as we move forward here, and hope everybody has a great rest of their day. And with that, we'll wrap up. Thank you.